Hi everybody, this is Matt Ingram continuing with a series of videos on generating LISA values, more specifically on estimating different methods for estimating the significance of these LISA values, and by extension of visualizing LISA values in the form of cluster maps, or what some folks call Moran scatterplot maps. There are two main categories, as I mentioned in the first video, for doing this, for estimating the significance of LISA values, and those two categories are the permutation approach and the numerical approach. We'll work through different software environments in executing these different methods. So the empirical example we'll be working through to demonstrate these methods is a piece that was published in 2001 in the journal Criminology, the top journal in the criminology or criminal justice field, by Rob Baller and his co-authors, including Glenn Dean, Steve Messner, Luke Anslin. And then we're going to do this, we're going to implement this in three different environments: in Geoda, in Python, and in R. Geoda and Python use the permutation method, and then we can implement the numerical method in R. You could also program R to implement the permutation method, and vice versa, but we'll just demonstrate the different methods in these different environments as noted here. This video will be very applied and practical in nature. We're going to go through the implementation in the different software environments, programming environments. So we will not be covering much of the technical detail underlying the methods. However, I do refer you to the additional reading noted here for that additional reading with regards to the numerical approach and some comparisons among different approaches. I would refer you to Dan McMillan's work and to Roger Bivand and his co-authors. And for the permutation approach, I'd refer you to Luke Anslin's work dating back to the mid-90s. Right, so the first video covered Geoda. We've already covered that, and that's posted online for your reference. Let's move now to Python and execute the same permutation analysis, essentially, that's underlying the analysis in Geoda, and then compare the results, or the resulting cluster map between Geoda and Python. They should be the same. So moving toward Python, this is our Spider editor in which we've been working. And I'm going to quickly move through. I assume you've loaded Python, you've loaded PySal, the spatial analysis library, into Python. If you haven't done so, here are some helpful notes and some helpful commands. Moving farther down the script, this is essentially replication 1 from the spatial analysis class. I expect you to import PySal. And remember that in the Spider editor, you can highlight the relevant syntax and then hit Control-Enter. You can see over here on the right that it executes the command. I won't execute all of these commands, but I assume that you've imported PySal. You've also changed your working directory, as I've noted here. So you need this code block here to change your directory. I've got several different working directories listed here. These are my working directories, but just make sure you change it to your own working directory. I've got some various replication data listed here from the first 3 replications we've done. You can check the path, that the path exists to the relevant shapefile for the Baller et al. Data. It's this NAT, or national shapefile. I've got various shortcuts here. This is all just review, but there's various shortcuts or ways of loading data listed here. Here is the final shortcut, here lines 157 through 163. And then we walk through working various spatial weights. Remember that the piece that we're replicating here, or that we're using here as an empirical exercise, uses a 10 nearest neighbors shapefile. And there's various ways to generate that shapefile using different distance calculations. So let's just use the Euclidean distance. This is the first one here. And then we want to transform that spatial weights matrix to a row standardized version. There are various options here, but I'll leave you to play with those options if you like. There's some other syntax that we don't necessarily need right now for creating spatial lags, and then for examining global spatial dependence, but all of this syntax is here from the original replication 1. Let's skip down to these local indicators of spatial association, or the local Moran. So if you haven't already done so, import the required packages. And then we have an example here from Serge Ray, but our own empirical example starts below and is highlighted here. So we want to set the random seed, identify our spatial weights matrix, which we have created previously. So we're just making W equal whatever you called your spatial weights matrix. So I'll just hit Control R here, and we see that with the command N, we're just getting the dimensions of our spatial weights matrix. You can see that over here. It should be 3085. That's because there's 3085 counties in the spatial weights file, or in the shape file. Now we can load our data and generate our Y variable, and then I'm generating this LM object with the command PySal Moran local based on this variable, using W as our weights matrix, transformed into row standardized. We're using 999 permutations. If you add one, that makes 1,000 permutations. If you remember from the Geoda map, that's what we used to generate this LISA cluster map. So we basically want to replicate this map that we generated in Geoda in Python. And then we want to make sure that we generate Geoda quadrants, not the Python quadrants or the other quadrants. Basically, we want to make sure that 1 identifies high-high, 2 identifies low-low, 3 identifies low-high, and 4 identifies high-low. So if we execute all of this, we highlight that and hit Control Enter, you can see it execute on the right. Then we want to generate the local Moran object, or LM object. You can see it execute there on the right. So it just did your 1,000 permutations right there. If you do directory for any object in Python, it'll give you a range of commands, or the set of the directory of commands that you can execute, ways in which you can manipulate this object. So you can see that we can extract various components of this object. So we want to extract the quadrants, the p-values from the permutation approach, and then some adjusted or standardized p-values. So let's make Q equal the quadrants, and check the shape of Q. So let's make Q equal quadrants. The shape of Q it's got a dimension of 3085. So let's make P our first permutation-based p-value, and then generate our adjusted p-value. If you had any questions again for which ones these were, you can look this up online and look up the literature on the package on PySal. So we could print Q if you wanted, just to take a look at what it looks like. You can see it prints a few values, the first 3 values and then the last 3 values. It looks like it has the right range. What's the minimum value of Q? It's 1. What's the maximum value of Q? Is 4. And you could, for instance, say what's the median value. So here we want to fill in, or create a new variable that identifies only those significant quadrants, right? So Q has all of the quadrants regardless of whether they're significant or non-significant. So let's make, this is a command here just to identify the significant value. So we're basically going to generate a new object called QSig1. And then looking at our the P that we generated, our p-values based on the permutation approach, we're going to only identify those where P is less than or equal to 0.5. Probably just want this less than to 0.05. And then we're going to append that quadrant if it equals to 0.05, if the p-value is less than 0.05. Otherwise, we're going to make that new variable q_1 equal to 0. So this is going to take q, which had a range of 1 to 4, and it's going to generate a new variable q_1 with a range from 0 to 4 instead of just 1 to 4, with 0 identifying the non-significant ones and 1 through 4 only identifying the significant quadrants. So again, that's this entire block. Control N, see it execute there. We could print q_1 if we wanted to. You can see now that there's several of the q values have been replaced by 0 where those are non-significant. And we could look at some other distributions here or change the structure of the object. For q_2, we could make it, we could use, generate make the same transformation, but now based on the adjusted p-value. That would be p2 is this value up here, which we made equal to the adjusted p-value. And here is the code block where we would basically do that transformation. Slightly different results, as you can see. Slightly more conservative, you might say. Here's another sequence for doing basically exactly the same thing. Another code block, so that's another option. You don't need to execute that if you've already executed the code block that we've just done. So now this section that follows writes our new data to the DBF file. So we're basically going to take the new variables that we've just created, q, q_1, q_2, and append them or add them to our existing DBF file from the shapefile. We probably don't want to copy over the file, so we want to generate a new DBF file and a new shapefile, and that's what the command structure below does. So I won't run through all of this, but if you import all of these packages and then define this function, append column to DBF, all you would need to do is highlight this entire code block here, and that'll define that new function append. It defines this new function append column to DBF. You're appending a new column to DBF. Let's just run it all. And here is an example from Nicholas Malicia from GitHub at Arizona State. But now here is the command with the Baller et al. Data, right? So we want to call the input shapefile or the input DBF file natdbf. We're going to create a new DBF file called natcopy. We're going to add this column quad to it, and these are column specifications, right? So the numeric type, the length, and the precision, the number of decimal places, basically. So we could run through all of this. Basically, if we run through this, we just created a new DBF file called this. We can now check to see whether the new quad column was added to that. So we want to open this natcopy DBF and then look at the header, and we should see quad at the end, and indeed there you see it down in the console to the right. You see that the column quad has been added to the previous DBF file. So now you can create a new shapefile. It should have already been created, but if you hadn't added that part to the definition file, you could copy a shapefile. But this part that I'm highlighting now should have already been done as part of the append column to DBF command. So here we are again. We could now take that natcopy DBF, create a new file called natcopy2, and add q_1. And so on. We could go on and add q_2 as well, and eventually we'd end up with a shapefile with the quadrant, which quadrant column, which includes all significant and non-significant quadrants, cluster identifications, right? Then we've also added a column qsig1 with the basic permutation generated p-values used to identify the significant from the non-significant clusters, or LISA values rather. Same thing. And then a third column, qsig2, using the adjusted p-values to identify the significant LISA values or clusters. Here's some code here to add a projection component to a shapefile. We'll skip over that. And then what we want is this mapping code now that appears here. This is borrowed directly from Serge Ray. If you skip down and add, I'll make sure that all of these packages are imported if you haven't already imported them. And then you want to define several commands. I would just suggest you highlight this entire block of mapping commands. It's fairly long, but it's better to have them all defined in case you want to use some of them or not. But basically we want to define all of them, even though we're using basically 3 of them. But just move down and highlight all the way down to where it says end of mapping on line 1409 and execute that. That'll define everything in that block. And we just want to return down here. And we basically want two commands here. We need for the LISA cluster map, we need this map projection, so we need to create a map projection instance. So you use the map projection command that we just defined. So we're going to use this coords command and generate a map projection instance from the shapefile nat_shape. So highlight that block from 1422 to 1425, hit Control Enter. We've now generated that. We've generated this object coords. And you can just check to make sure that it's all correctly formatted. And then this is the LISA cluster map command that we just defined up above in the mapping section. If you scroll up to line 1262, you can see that here is where we defined the LISA cluster function. And so now we want to execute it, right? So we need these arguments. We need a map projection instance, which we just created. We need the LISA object, which we created earlier. And then we just need to title our map and give it a p value. So this is, we're back down here. We just created our map projection instance with this code block. This is our map projection instance. And now we're going to use this command here to project a map using the coords object, the LISA object, which is LM. We're giving it a title, map cluster, and we're going to use a 0.05 cutoff here. So if we hit Control Enter, that should generate a LISA cluster map, and there it is. So you can see that it's essentially the same as our geoda map. This is our geoda map. I'll shrink it down here so we can see them side by side. But we've basically got in the geoda map a large cluster of low counties across the top of the United States, and we see that in the map created by Python, and then a large segment of high clusters across the southern part of the United States, including all of Florida, and we see that mainly here. Those are the two biggest patterns. We see some high clusters in Texas and the northern part of New Mexico, and we see those also in the map created in Python. There should be some small differences. There should always be some small differences across the two maps. since there's this randomized shuffling that's taking place with each permutation analysis. But they should be substantially similar, and they are. So that is how you generate an estimate of significance for the LISA values in Python. Here we're comparing it side by side with a map generated in Geoda. And now let's move to R to consider the methods for generating LISA values and estimates of their significance using the numerical approach advocated by, among others, Roger Vivan. Thank you.